Hi, Bobcats. In this section, we're going to take a look at precipitation reactions. These are like the dissolving, the solubility reactions, but in reverse. When a substance dissolves, you start with the substance in the solid phase, and then as it dissolves, it ionizes, and you get cations and anions, and they'll be in the ratio specified by the stoichiometry of the formula in order to get charge balanced. You have the formula has to have an equal amount of positive and negative charge. But in the case of precipitation reactions, the cation and the anion are coming from different places. You'll very often in these problems start with the cation in one solution and the anion in a different solution, and then you combine the solutions. So there's not a fixed ratio between the cation and the anion in terms of the solution concentration. Then what we will do is figure out, all right, what concentration would these ions have in solution? That will let us calculate a numerical value for Q, the reaction quotient. If Q is bigger than KSP, then the compound will precipitate out. If Q is smaller than KSP, then everything stays dissolved. Because if it were possible, the reaction would go in the forward direction, and so if any solid were present, it would all just dissolve up until Q equals KSP. All right, so let's take a look at some concrete examples. Our objectives are to look at this relationship between the reaction quotient Q and the solubility product constant, KSP, and then to see if we can use some of these ideas in order to selectively precipitate a particular ion out of a solution. Okay, so the precipitation reactions belong to a category of reactions that are known as double displacement. Some people call these double replacement, and some people call these metathesis reactions. We basically have two ionic compounds that swap partners. The ionic compounds have to have a positive ion and a negative ion, and so when these two compounds react, they simply swap partners. And we get precipitation if one of the products happens to be a solid. So we start with everybody on the reactant side is aqueous, but then one of the products will be a solid. Yeah, and so for this reaction to actually occur, there has to be a driving force present, because it is possible for many ionic compounds that if you mix them like this, nothing happens. You start with two solutions that look like water, and you end up with a combined solution that just looks like water, because nothing took place. So one of these driving forces is precipitation, or the formation of a solid. And it's really helpful to think about this as being like solubility in reverse. We'll have ions that come together in solution, and then that KSP reaction goes backwards in order to produce the solid. So when precipitation takes place, the ions that come together to precipitate will come from different sources. In this case, the example that's shown here in the diagram, lost my pen, here we go. One of these chemicals is coming from the beaker that's down below. Let's say that particular beaker has potassium iodide, and then this beaker up top would have the other reagent, which would be something like lead nitrate, because that solid that's being produced with that bright yellow color is clearly lead iodide. And so the lead ions are coming from one beaker and can have any particular concentration, and the iodide ions are coming from the other beaker, and they can have a completely different concentration. And then when they get together, we have to determine what Q is. If Q is equal to KSP, we're right at equilibrium. That pretty much never happens. If Q is greater than KSP, then precipitation occurs until we've lost enough ions out of solution that Q equals KSP, and then precipitation stops. If Q is less than KSP, if there happened to be any solid present, then it would continue to dissolve until Q equals KSP. So this is our first numerical example involving precipitation. The KSP for gadolinium hydroxide is 1.8 times 10 to the minus 23. If a solution is 0.01 molar in gadolinium ion, and the pH of the solution is slowly increased, at what pH will gadolinium hydroxide begin to precipitate? Okay, so the KSP reaction that we are interested in here is gadolinium hydroxide, and it'll be in equilibrium with gadolinium ions, whoops, left off the D. So gadolinium ions, aqueous, and hydroxide ions, aqueous. Now for this to be a balanced equation, we've got to put that coefficient of 3 in front of the hydroxide ions. Now, we are told that, well, okay, let's go ahead and write the KSP expression before I start plugging numbers in. KSP will be gadolinium to the first power times hydroxide cubed. Now, remember, the hydroxide ion and the gadolinium ion are coming from two entirely different places. What we're told about gadolinium is that we have a solution that is 0.01 molar in gadolinium plus 3 ions. We have no idea where that's coming from. That could very easily have come from a gadolinium nitrate solution. Nitrate tends to be the ion of choice when we're trying to get a soluble metal or a soluble compound of a metal. And then if the pH is slowly increased, that means we're adding hydroxide. So the hydroxide ion is coming from somewhere else. So when we start to plug numbers in here, we're trying to figure out what value of hydroxide will make Q equal to KSP. Well, we know that KSP is 1.8 times 10 to the negative 23rd. Gadolinium is 0.01, and then hydroxide is the thing that we are looking for. Now notice I'm not putting in 3x here for hydroxide. Essentially this is just x, because we don't have to keep that 1 to 3 relationship between gadolinium and hydroxide, because they are not coming from gadolinium hydroxide dissolving. Instead, gadolinium is coming from something like gadolinium nitrate, and then hydroxide is coming from whatever way we're increasing the pH of the solution, which could literally just be like chunking in a sodium hydroxide pellet and letting that dissolve. So to solve for hydroxide ion here, I need to divide both sides of the equation by 0.01. So 1.8 EE23 negative divided by 0.01 is going to give me whoops, that looks like a negative sign. I'll erase that in a moment. 1.8 times 10 to the negative 21 is equal to the hydroxide ion cubed. And let me real quickly erase that mess so that that doesn't look like a negative over there. And so then in order to get the hydroxide ion concentration, we would take the cube root of both sides. So second, the x root of y, I'll type in a 3. And now let's flip that back over to scientific notation, and I've got a hydroxide ion concentration of 1.22 times 10 to the negative 7. From this hydroxide ion concentration, the easiest thing probably is to calculate pOH. So I'll take the log, and pOH will be 6.91, and then pH would be 14 minus that, and that's going to give a pH of 7.09. This pH is just barely over neutral. So just as soon as the solution flips to being basic, gadolinium hydroxide will start to precipitate. All right, on problems like this next example, it really helps me to draw a picture to kind of illustrate what's happening. This says, assume that 0.1 molar sodium fluoride solution is added slowly with stirring to a solution that contains 0.1 molar chromium nitrate and 0.1 molar calcium nitrate. Which salt, chromium 3 fluoride or calcium fluoride, precipitates first? The KSPs are given. So here's where the picture really helps me to figure out what is going on. We're going to have a beaker here, and inside of this beaker, yeah, I know I'm not very good at drawing beakers, but hopefully you get the idea. We have inside of this beaker 0.1 molar chromium ions, right? That is coming from our chromium nitrate. The nitrate's a spectator ion. It's just there to give us a nice soluble source of chromium ions. And this beaker is also 0.1 molar in calcium ions. That's coming from the, spanning two lines here, but the 0.1 molar calcium nitrate. Again, the nitrate just makes the calcium very, very soluble. So we've got this beaker that has these two ions floating around in it, and we're going to start adding to it fluoride ions. Those fluoride ions are going to be coming from a separate source, a separate beaker, and it's really kind of irrelevant that it's a 0.1 molar sodium fluoride solution for this particular problem. It's just going to be a source of fluoride ions. Now we've got two relatively insoluble salts, chromium fluoride and calcium fluoride, and we just need to try to figure out which one of these will precipitate first. So think about this. The fluoride ion concentration starts off at 0 and then it increases as we add more of the sodium fluoride. So we want to see which one of these compounds, chromium 3 fluoride or calcium fluoride, will precipitate at a smaller fluoride concentration. That's the one that will precipitate first. So on this slide, I'm going to tackle chromium, and on the next slide, we'll tackle calcium. So we are going to have chromium 3 fluoride solid in equilibrium with chromium ions plus 3 fluoride ions. And so our Q or our KSP expression is going to be chromium times fluoride cubed. And KSP for chromium fluoride was 6.6 times 10 to the negative 11. The chromium ion solution concentration is 0.1, and then the fluoride ion concentration is what we're solving for. So I'm going to divide both sides of this equation by 0.1. So 6.6 EE11 negative divided by 0.1 is going to give me 6.6 times 10 to the negative 10 is equal to fluoride cubed. And so now I'm going to take the cube root of both sides of this equation, and that's going to give me a fluoride ion concentration of 8.7 times 10 to the minus 4 molar. This is the concentration of fluoride ion that is necessary for chromium 3 fluoride to precipitate. All right, on the next slide, we'll calculate the same thing, but for calcium fluoride, and we'll see which one is smaller. Whichever answer is smaller will be the one that precipitates first.